Hi, my name is Stuart Nick. I'm with the Odds and Metallurgical Society. So I'll be reviewing a paper today. This particular paper is called The Design of Copper Cooling Systems for Copper Smelting and Converting Furnaces. So this one was written by Hugo Juba with Ternova Pyromet. And you can access this through OneMine. So to get a copy, log into the OSM, go through the members area, go to OneMine, go through there, and you should be able to find it there. So this particular paper is one of those really interesting ones that you sometimes see people doing in industry. So it's a bit of a story here. So a lot of smelting furnaces, you have multiple parts to the lining system itself. So you've got first of all, you've got the molten bath is contained by a refractory or a freeze lining system. Then you have a binding or a steel shell system. So depending on the furnaces, they're either completely refractory, a mix of refractory and copper cooling systems or other cooling systems, complete cooling systems, and they always have a steel binding system. So commonly what you'll see out there is people who have refractory systems sometimes try and put water on their steel shells to try and improve the furnace campaign, thinking it will cool the slag down at the hot face and extend the campaigns. So this has got some good maths to explain all this one. This is a really neat paper, really good one. So commonly people will go out there, and you could sometimes see these in smelting furnaces. They'll go out and they have all these spray coolers on these furnaces, and you go, well, is that necessary? And lots of people think it is, but Hugo goes through some really cool maths, and you can see it all. So he presents and goes through these 1D steady state heat transfer equations. So back from your uni days, those heat transfer calculations are really important for smelting design and things there. So this is for a simple planar system. So you can see you've got a 50mm steel shell, you've got a backing or an insulative lining, then you've got your working lining. So they've got different bricks for these ones. So this is generally a mag chrome brick for non-ferrous pyrometallurgy. You have other brick systems and other commodities. You've got your insulative lining, which won't resist your slag components, and your steel shell. So in this particular case, scenario 1 and scenario 2. And so in this one, you can see at the start of the campaign, you have a hot steel shell about 300 degrees Celsius. And as you eat up the brick, your thermal gradients change and your steel shell temperature increases. The general rule of thumb I've heard for steel shell is you want to keep it below 300, 350 degrees Celsius. If you start to creep up, the steel shell starts to glow and it starts to deform. So glowing is what the general rule of thumb is. You go out there and you start to worry if it starts to glow. You can do things there. So you can see here that this is the hot face, this solid black line, and the blue temperature that's your freeze temperature, and this is the temperature. So in this particular system, you have a superheated slag, and you can see that this hot face is just above the freezing temperature. And that hot face, by being above the freezing temperature, can dissolve slowly in the slag. And so when you go from this to this, you can still see it's slightly above it. And so it just keeps on eating away slowly. So you can see that steel shell 300 to 500, hot steel plate towards the end of the campaign. People can sometimes get a bit concerned there, but you generally start to re-brick after certain conditions. The other next scenario is what if, rather than having just a bare steel plate, you cool it with a water cooling system? So looking at the maths, if you go through the 1D heat transfer stuff there, you can see that this steel plate, when you put water on it, it does not change too much between the start of your furnace campaign and the end of your furnace campaign. So that steel plate temperature is lower, but doesn't change. You suck more heat out of the furnace, but when you go through the maths, you can see that the hot face of the brick still gets eroded away. And so from this, the driving force of the solution is here and not the slope. So sucking more heat out of the furnace, you can see here, does not lead to slower refractory corrosion too much. May have a small impact, but it's not really that big. It just changes its steel plate temperature, so you don't really get much benefits from it. So this is really cool maths, because this sort of goes through the fundamentals as to, does it make sense to put water on your steel shell to improve your campaign, or do people add water and things there for other reasons? So just the simple logic of hotter furnace eats bricks faster, make the bricks colder, make them last long, lengthen them out. The simple logic does not apply. You sort of have to dig through these maths, and Hugo goes through this really neatly. He goes through all the little equations, and so you can go back through all these things, and he's got the bricks and heat conductivities and things like that. You can work through this yourself, and it's probably a really worthwhile exercise if you are interested to working through all the maths behind it. The other one, of course, is he goes through these water cooling elements, and that's a different case. So these ones here, you got these copper elements, and you can see with these ones, you can see that the hot phase temperature of the castable is below the temperature of the bath, and by being the hot face being below it, you're going to freeze material on, and you're going to form that freeze lining. And so as that castable changes, so at the start of the campaign, you may have some castable, you may knock it off. You do have a bit of a change there, but that freeze lining is always there. So theoretically, you should not be eroding away your copper coolers. They can be damaged for other reasons, but this is really neat because it shows that this one here, when you suck out enough heat and you get to the point where that hot phase temperature is below the freezing temperature, then you form the freeze lining. But just the simple brick systems, you may not be able to do that with just adding water there. So there's a sort of a crossover point. You sort of have to have either a refractory or a freeze lining. You can't sort of try and do a refractory with a freeze lining very easily at all. There are some sorts of chemistry tricks and things that you can do. Some of the furnaces that I work on, we've got these advanced chemistry systems and things there, and we can get these really, really long campaigns. But that's more through other means and methods there. But yeah, so it's also really interesting because copper coolers aren't always the answer either. Sometimes these brick systems are better, lower cost, faster rebricks, and you can get really good campaigns if you can control these sorts of things well. So yeah, really good paper. Check it out. It's on OneMine. It's called The Design of Copper Cooling Systems for Copper Smelting and Converting Furnaces, written by Hugo Joubert. Good fellow. If you see him around, you can ask him lots of questions. Really clever. So yeah, thanks.